These are the lecture notes for Chapter 2 on chemistry, and we covered ionic bonds in the last recorded lecture. Now we're going to cover covalent bonds. So what has happened here, let's just look at the oxygen atoms because they've got more electrons. If you notice the yellow colored electrons on the left in the outer energy level, there's going to be 1, 2, 3, 4, 5, 6 of them, because the atomic number for oxygen is 8. So that's 1, 2 in the first energy level and 6 in the second. And then if you look at the oxygen on the right, its electrons are done in orange, but there's still 6 electrons in this outer energy level. So each oxygen needs 2 more. So if they share 2 with each other, that comes out to be a total of 4. And that is 2 pairs of electrons that are being shared. So when you actually write that, you would put 2 oxygen atoms, and in between them you'd put a double line, because that's a double covalent bond. But that gives them 8 electrons each in their outer energy level. Okay, so covalent bonding are the strongest chemical bonds. Ionic bonds are next. Now, there are 2 types of covalent bonds. In these examples that we looked at on this page, all of these are called, so non-polar covalent bonds are formed when the electrons are shared equally, but there are also polar covalent bonds where even though the electrons are shared, they're not shared equally. One of the atoms in the molecule has a slightly stronger pull on the electrons than the other one does. So you end up with one end of the molecule having a slightly negative charge and the other end having a slightly positive charge. And this is how a water molecule is arranged. Well, this is showing hydrogen bonding. It's not showing a polar covalent bond. There's not a picture for that. So, looks like I'm going to have to draw. All right. Well, you can see it in this picture. The water molecule is composed of 1 oxygen and 2 hydrogen atoms. The oxygen ends up with a slightly negative charge. The oxygen end of the molecule. The hydrogen end of the molecule ends up with slightly positive charge. See, and the hydrogens are kind of pointed away from the oxygen. So they're at one end, whereas the oxygen's at another end. So you end up with a negative and a positive end of the molecule, kind of like you have with an ionic compound. So when there are several different polar covalent molecules, but what this does is it allows water to have a lot of properties. It allows it to form hydrogen bonds with other water molecules. Notice how if you look at the water molecule here that I'm pointing the eraser at on the left here, the oxygen end is facing or lined up with the hydrogen end of the other water molecule. So basically you have all these slightly negative and slightly positive charges, and the opposite ends are going to be lined up facing the other opposite end, of the molecules. And you can look at that, and that's what holds water molecules together, so that water forms like raindrops form. And instead of just water coming down as a sheet, it comes down in droplets. And it beads up on your car windshield. Water droplets form because of that. And hydrogen bonding gives water a lot of properties. It gives water the property of surface tension. And that's the attraction between water molecules at the surface of a body of water. And it allows insects and spiders to walk on the surface of the water. Okay, checkpoint question. Which kind of bond holds atoms in a water molecule together? And that will be a polar covalent bond. And the attraction for water molecules to other water molecules is called a hydrogen bond. That's real important. So the bond that holds atoms in a water molecule together, it's holding the oxygen and the hydrogen atoms together. That is a polar covalent bond. And the attraction of water molecules to other water molecules is a hydrogen bond. Okay, now for chemical reactions, we're going to learn really two basic chemical reactions that we're going to learn. But you need to know some terminology. The reactants, which would be the substances that are going to react, that are going to combine and recombine with each other to form new substances. So the ones that start out the reaction are called reactants, and then what's formed after the reaction proceeds is called the products. And the word metabolism is the sum of all the chemical reactions in the body, whether those reactions are breakdown reactions or synthesis reactions. All those reactions are called our metabolism. And then chemical notation, like for here you have the chemical formula for glucose. This tells you that there are 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen in one molecule of glucose. All right, energy is the capacity to do work. There are 2 types. The energy of motion is kinetic, and stored energy is potential. When we're dealing with chemicals, potential energy is stored in chemical bonds, and then it can be released as kinetic energy when the bonds break. And even though energy cannot be created or destroyed, it can be converted from one form to another. So sometimes when we lose energy, we're really not losing energy. It's been converted to heat. It's been released as heat into the environment. So there are 3 types of chemical reactions important in the study of physiology. Really the first 2, honestly, are the only ones that we talk about much. The only exchange reactions would be like the buffer reactions, and I will probably mention those to you. But the first 2 definitely you need to be very familiar with. A decomposition reaction is a breakdown reaction. And then a synthesis reaction is a reaction that takes smaller substances and builds larger molecules with it. So specifically, our decomposition reaction is called hydrolysis, because what it does is it takes this chemical AB, A and B are just representing a chemical made of A and B, because there's no A and B on the periodic table. But it's just letting you know there's some chemical made of elements A and B that's being broken up into the individual elements A and B. So AB is being broken up into A plus B. And since AB, the chemical AB, contains, or doesn't contain, I'm sorry, since the chemical AB needs water to split, what happens is one of the hydrogen atoms bonds with the A. The other oxygen and hydrogen bond with the B. So you have a hydrogen atom bonding with the A, and then OH is hydroxide. You have a hydroxide that bonds with the B. And by doing that, it breaks up chemical AB. Anyway, that's a hydrolysis reaction. And catabolism is all of the hydrolysis reactions in the body. And definitely the reactions where we break down the food we eat are good examples. All right, then we have dehydration synthesis, which is opposite. Now you have your chemical A, or your substance A, which is bonded with a hydrogen, your substance B, which is bonded with a hydroxide. You have the removal of the H and the OH, and they're formed together as water. So water is a product, And then you have linking A and B together to form chemical AB. That is a synthesis reaction. It's called dehydration synthesis or condensation because the water molecule is removed. And it is one of the examples of anabolism, which are all of these synthesis reactions in the body. The synthesis reactions require energy, whereas the breakdown reactions release energy. Exchange reactions, if you notice here, you've got chemical AB and then chemical CD, and the D and the B switch places. They exchange places, and you get AD and CB. So there's new substances that are formed, but the reactants and the products are the same size. You don't have a large molecule being built or a smaller one being broken apart. You just have reactants and products are the exact same size. This is probably not meant to look like that. Let me try. I'll try to fix it. Let me see here. And show. Okay. Yeah, I can't go in this, but what I can do is I can delete it and I can make it like it's supposed to be. Insert text box. A plus B, and then we're going to do an arrow with two ends. I think that would work just fine. Okay, so, and we'll make it a bigger font. All right, so basically you have two opposite arrows. They can either be one on top of the other, or they can look like that with the arrow at either end of a line. But anyway, it's just showing that the reactions can happen. The reaction can go in the forward direction or in the reverse direction, either way. And when this reaction's at equilibrium, there's an equal amount of AB being made as there is A plus B being broken down, as there is being broken down into A plus B. So there's going to end up being, like if you have this reaction going on in a beaker, there'll be equal amounts of reactants and products because you'll be forming product at the same time you're forming reactant, and that's equilibrium. That's when equilibrium is reached. All right, checkpoint question. Using the rules for chemical notation, write the molecular formula for glucose, a compound composed of 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. Well, let's just go back to the glucose that's already here. C6H12O6. All right, let's see. Question number 8. In living cells, glucose, a 6-carbon molecule, is converted into 2 3-carbon molecules. And this type of reaction is a breakdown. So if we go back to our page, it's a decomposition reaction. It is specifically a hydrolysis reaction because it is breaking apart a larger molecule by adding water to it. So, and it's one of the reactions of catabolism. So it's a hydrolysis reaction. When glucose is broken down into 2 3-carbon molecules called pyruvic acid or pyruvate. The breakdown of the glucose is a hydrolysis reaction. That's what you need to know. If the product of a reversible reaction is continuously removed, what will be the effect on the equilibrium of the reaction? Let's go back to our little equation. All right, so if I keep removing this, if I keep removing it, then it's going to cause the reaction to go in the forward direction. It's going to cause A plus B to keep making more product. If you take it away, so let's say this reaction is going on in a beaker, and every time AB forms, I can remove it. I can easily remove it from the beaker. I take it out of the beaker, so there's more A plus B in there. And so that reaction is going to continue in the forward direction, not the reverse direction, until equilibrium is reached.